but we have 2 hours for the workshop, and if you just start with, I should say, a lower cutoff rate, it may take 3 hours. Then you have to have your laptop, go home, and come back sometime soon.
Excuse me?
Yes?
So what do you want cut out? The features?
The features which they have standard deviation less than the 95% on your, I should say, gene expression profile state. It's your choice, you can choose anything. You can just, for example, start with 75%. Still 75% is very stringent, it's very strict. 95% is for the sake of saving some time. Huh? And also if you see, I have, I should say, $E set. It's always crucial as a template for you for machine learning. By doing that, you are only extracting the gene expression profiles. Because what is the plan? From the gene expression profiles, you are going to find the type of the cancer in machine learning. That's why you have $E set. Then filters your gene expression profiles. I'm just going to click and enter. And now I'm so glad that it works. Sometimes working with bioconductor is so challenging. The function which used to work 2 minutes ago, it stops working. Okay. And now you can just take a look into the data sets by the view. And you can check the class. The class is expression set, which you are so happy. That's what we expected to have. You're looking for the gene expression profiles. Because the mind map is that starts from the gene expression profiles in microarrays experiment to find the cancer. From the genotypic data, go to phenotypic. That's what you do in machine learning. Okay. Any questions so far? Because we finished step number 1. Well done, everyone. Well done. You filter out lots of information. It depends on the, I hope that people choose a different cutoff rate, because we're just going to go back to just work with those information which you have. And we share the information with different cutoff rates. Okay. And now, I just go back to the slide. Yes?
Sorry, I just tried to run the filter function, the filter function, and it requires like a package for the array chip type. Are we supposed to install that?
That's right. Whatever it asks you that you have to install, search it on Google, find the command line, and just run it. It happened to me a lot. Sometimes some packages it is not initially installed with the R. Once you install it, then just run the command.
Yes. Follow-up. So, if different microarrays have different chip types, do you have to install separate packages for that?
It hasn't happened to me. It doesn't matter what kind of technology you use. The algorithm is, I should say, universal for any kind of technology. Okay. Now we are going to the step number 2 to transform the data set. Any questions so far? Nothing? Then let's continue. By the way, whenever you feel exhausted, we can just have a quick break. Everyone was able to install the packaging filter? It worked for everyone? Yeah?
There's something like on the Windows system set HGU and weird name.
Yeah, you have to install that package also. This is going to be for human genome data sets. Copy paste that, it comes with .db, huh?
Yeah, .db.
Yeah, please copy paste the whole thing. Just go to the Google, find the biopsy manager command to install it. Normally the workshops for the cancer genomics, it requires, I should say, at least a couple of days, but we are just going to have as a kind of a taster for just 2 hours. That's a package which you're looking for, huh? HGU 95AV2, huh? Okay, now let's go to the second step. Hopefully, just the gene filter just worked well on my, I should say, the system, because it's a very tricky, I should say, function and package. Sometimes works well, sometimes you have to rerun. Okay. Let's go to the second step. The second step is that you transform the data sets. Okay? In order to transform the data sets, we just mean that we just want to scale them. Because when you just work, let's say, for example, for the data sets which you have, let me go to show that to you. If you go to, let's say, for example, go to say data, you just go to the expression, and when you run it, you will see that it shows some kind of crazy number there. Then we do not want that happens. We just want to scale the data sets which we just created. Then in order to do that, we just want to write a function in order to scale and standardize your data sets. Put every microarray expression, stand something between -1 and +1. That's the plan, which we're just going to do right now. Question? Yeah. Okay, the function which you have, I have written that for you. You can find it, I should say, on the I should say, the GitHub. The function is in order to, I should say, put that thing on the scale. It's a very, I should say, basic concepts in statistics. For example, you just want to standardize the data sets which you have, the distribution which you have. What you do, you have your, for example, x as a kind of samples minus any measure of, let's say, the central tendency. You can choose as a median, divided by, let's say, standard deviation or interquantile range. That's one of the basic concepts in statistics. And you use always that in cancer genomics in order to scale everything, transform everything from your microarray data into, I should say, something scalable. And in order to do that, I have written a code here, and I have written a function. The function, for example, I just put that ESET. The function's name is ESET, and it stands for raw interquantile range. What does that function do? It just goes to the matrix of, I should say, gene expression profiles, which you already filtered it to find, I should say, each row, find the median, find the standard deviation or interquantile range, and divide these two together and return it back to you. That's how you scale your function. You can always have this formula as a template. You can always use that in any context in gene expressions. And also you see that I compute, I should say, the log quantile, which is going to be the first, I should say, 25%. I'm just going to put 25% there. And also, I just find the upper quantile. I'm just going to go for the 75% of your data sets. And it seems everything is ready. And at the end, when I have measured the lower quantile with the upper quantile, 75%, 25%, I'm just going to subtract it. And that subtraction, it gives me interquantile range. That concept sounds familiar to you? Interquantile range? Yeah? Everyone is happy with that? Yeah? Interquantile range? Yeah. Then what I'm going to do is to run this function. And the function is readily just applied. Okay. And now, I just come to the second line. You can use it as a kind of template all the time when you just work with the gene expression profiles to standardize or scale your microarray, I should say, gene expression profiles datasets. Based on the function which we created, I'm just going to call that this time x, because we use a different name for the functions ESET, which stands for expression set. I said that whatever x is that, the function comes to subtract from it the raw medians. It's, I should say, a package. It's a function with the R for any, I should say, rows which you have in your matrix. It comes to find the median or the average of it. And divided by the raw interquantile range, which is essentially the function, and that thing which you see at the denominator, it is essentially the function which we created earlier. You will see that raw interquantile range, and I have raw interquantile range. Actually, with that function, we found, I should say, that interquartile range. I'm just going to click and run it. Okay, I hope that this line just gets, I should say, run, because 50% it works, 50% it doesn't work. Sometimes you have to restart your R to just if it doesn't work. Hopefully this time works. Working with the gene expression profile is not easy. Let me see that if the function is installed. Okay, it's run it. Let's see. Okay, it just run the data sets, and as you will see, we have the gene expression profiles, I should say, installed, and we standardize it. As you see, I just called that, I store that into an option, which is called all phyla express, which is meant this is the expression data sets. But before that, something which I do not have to forget that to tell you, otherwise I should not just forgive myself. That's crucial when you just work with the gene expression profiles, and that's the functions. This is called express. And what does it do? Whenever you just work with the cancer genomics data sets, you are confused because of the different type of the data which comes with your data sets. Using that function, EXPRS, it just extracts the gene expression profiles from all the genome which is in your data sets. And I should say, just exclude any other data. And that's what you want. You do not just want to just know how the data sets, let's say, from the different type of the age or the sex of the patient. You just want to just work from the gene expression profiles to predict something. How you make the prediction? With machine learning or neural networks, just by way of gene expression profile. And that function is crucial because it works 50% of your way there. If you forget that function, you're screwed. Then always remember that function, express function, which extracts all the gene expression profile. We run it, and now we can also view the data sets which we have. It's going to take some time. You see that? I hope that it's working much faster for you. Okay. And now we are just going to a different topic. Any questions so far? Anybody has been able to get the, I should say, the gene expression profile, and you can view that? Everybody succeeded to standardize your data set? And if you see, or I should say, if you see, for example, if you just go to the view of, I should say, for example, the expression profiles, you see that my laptop, it takes some time to just upload it because it's computationally very expensive. But if you just go there and see that, you see all the numbers from your gene expression profiles stands somewhere between -1 to +1. And that's what you aim for, to scale it into that predefined scale. Otherwise, your gene expression profiles gets different value from, let's say, from 9 to +2, it's all over the place. But by that code, you have it standardized. Everything stands either between -1 to +1. We just work with cancer genomics, always that's the crucial step, to scale your information.
I got a question.
Yes?
You only have about 100 patients. How could you get so many rows in your data?
Because these are the gene expression profiles. 120 patients comes, let's say, at the rows. Imagine a matrix. The rows are patients. Patient X, patient Y, patient Z. But with the columns comes with that data set, thousands of the columns. Because each column shows the gene expression profiles from different chromosomes. And that's why the data set is inconveniently huge.
I mean, look at the rows. It's a lot of rows there. So you see that there should be thousands of rows.
Oh, if you're just looking for the gene expression, that's also, this is a kind of a variation comes with the gene expression profiles. That's why the data set is so huge.
You mean one patient will have multiple?
That's so true. That's why they call that Kirchhoff dimensionality. Your dimensions is a scope, it's so huge. Okay? And okay, now we're just going to the next step.
Excuse me.
Yes.
I'm checking the data, the kind of the all phyla express, and I still have values that are below -1.
Below -1, but this
Yeah.
is still how far they are from
-1.56.
That's totally fine.
That's still okay.
That's right. it should be something like that. But you will not see -2.
No.
-2, no, that's totally fine. Thanks for the question.
It could be much lower, like, because it only is a middle not the from max minus minimum, right?
Minus minimum mean, why this is,
We'll do normalization, right? You can just minus the max value, the difference between minus and the max and minimum.
Right.
oh, you mean the normalization,
Yeah.
that's right, that's normalization, we did the standardization. If you do normalization, that's true, but we did the standardization, they are two different. Max and mean, it's for normalization, we did the standard, but also true, if you just normalize, it also works.
Yeah, there could be some outliers where you were way
You're going to
below.
take the outliers by one of the algorithms. No worries about the outliers. But that's a good point, thanks. Okay, now we are just going, I should say, to one interesting thing, which is going to be, I should say, select the distance or similarity matrix. It's going to be very crucial. We're just going to cover that when we just take a break of less than 2 minutes. Then we come back to run the first algorithm of unsupervised machine learning. Okay. There are some, I should say, some criteria for the distance. We do not have time. I'm not going to go through that because when you define a distance, it has to meet 5 different criteria. We are not going to follow that. I'm just going to show you some, I should say, the metrics for the distance. For example, we have Euclidean distance. They do not represent a physical distance. They are a measure of the similarities. If you use Euclidean distance, which it means that the square root of, I should say, differences between 2 objects, it doesn't mean that you're finding the distance from me to, let's say, for example, to the fan. It's a kind of a measure for similarity. Also, you have Manhattan distance. It gives you a different result. For the same cancer data sets, different, I should say, distances produces different outcomes. You have the correlation based. You have Pearson. Forget about the maths, there is no time to go there. Cosine correlation. Spearman sample correlation. And Kendall's tau, we're going to use that, it detects the outlier and kills the outlier of the samples. And Kendall tau and Spearman also, Spearman and Kendall tau, I should say, they remove the outliers. And we have also one matrix. It is Mahalanobis. It's people who are from stats, they knew about that, I should say. Anybody from the stats department here from you after your year? Nobody from stats? It gives you very cool, I should say, outcome in your machine learning. We're just going to go through that. And also, that's the packages which you can find those distances. If we just want to use the tau and Spearman, you have to just go to install biodist from the bioconductor. Or if you just want to install, for example, Euclidean distance, you have to just install stats from, let's say, the R packages. And when you just install those packages, it's a matter of, I should say, a couple of seconds to find the distances and run the algorithm. Okay. Now that we are ready to just move on, unfortunately, we're planning just to spend much time on the distance because when you know what kind of distance, what kind of characteristics they have, when you just have your cancer data sets, the choice of different measurements of the distance gives you different outcomes and gives you different accuracy of your prediction. That's always, I recommend you spend more time on the distance than on the classifier algorithm. Okay, now we are just going to go to, I should say, do some cool stuff. If you just go to step number 3, we are now step number 3. What do you think if you just get 2 minutes break, then we come back to continue, huh? I see some people are yawning, and I thought that I'm boring a little, but I think that it's worth to just spend some time. 2 minutes or 3 minutes for the break. The washroom is going to be at the back, and come back, we just continue. Step number 3. Step number 3 is essentially a nice welcome to the first algorithm for KNN classification.